So chapter 7 starts out with clarifying a few things that we've maybe been a little loosey-goosey about last semester, okay? So we're going to kind of clarify them, and then we will do better going forward. So the first thing is parameter versus a statistic, okay? A parameter versus a statistic. What is the difference between a parameter and a statistic?
A statistic is when a million people die, and a parameter is the...
No. Parameters describe population values. So if I say, hey guys, what parameter are we going to use? Then we would be talking about the population. And if we are talking about statistics, those describe sample values. So if I were to tell you, for example, that 13 is the statistic for the number of hours teenagers spend on their phones.
Wait, can you repeat that?
If I say that 13 is the statistic, then is that about a sample or is that about a population?
Sample.
That's a sample. So basically, I took a sample and I looked at what is the average number of hours for that sample that they are on their phone. That's a statistic, so it's about a sample. If I were to tell you that 5'9" is a parameter, then is it about a sample or is it about a population? It's about a population. That's really all I'm saying here, okay? Easy enough? Perfect. What about the notations that go with that? So, samples are statistics, populations are parameters. We're going to use samples to estimate the corresponding parameters, okay? Now, some of these you guys already know. For example, a sample mean. A sample mean. Do you guys remember the notation for the sample mean? So we have actually used mu and the other one that I'm actually looking for here interchangeably. That's why we kind of need to clarify and then go do better going forward. Because we've been using mu and x bar a little bit interchangeably, which we really shouldn't have been doing. Because technically speaking, x bar is the mean for a sample. So we take a sample, we get an average for that particular sample. That is the x bar. Once I then use that number to estimate the parameter for the population, it becomes the population mean. And the population mean uses the mu notation. Okay? It's the details. It's the little details that will start now making a difference. Okay? So, I want to know something about the population. I want to know the average SAT score at McKinney Boyd High School. So I take a sample of 100 students from McKinney Boyd High School, and I get their SAT score. That is an X bar. The average of that 100, that is an X bar, because it's the average of the sample. But once I say that that sample is good enough because I did a very good random sample, I made sure there wasn't any bias, I did all of the thing, control, replication, blah, blah, blah. Now I can say that whatever that average is good enough to be the true population mean for McKinney Boyd High School. And now I'm going to say McKinney Boyd High School's average SAT score is mu. Because now I'm talking about the population.
So you can translate that small thing
Because X bar is estimating the truth, because most of the time I don't have time to take a census and get everybody's data.
Miss, how many margin of error problems are we going to do?
A few, but not until later.
Oh, okay,
Yes.
so this isn't the margin of error.
Not yet. Not yet. We're getting close, though. All right.
That's why
Um,
the population of Finland doesn't exist, is because their entire population is within the margin of error.
Interesting. Sample standard deviation. Sample standard deviation. You guys have seen the notation for this. What is it? Do you remember it? Sample standard deviation notation. S sub x. Very good. S sub x. Now, that is going to estimate the population standard deviation. We have used this notation interchangeably with S sub x. Sigma. Very good. Sigma. Now, there's one more that we're going to start seeing a lot of. And you guys will get very comfortable with it, but we haven't really done a lot with it so far. And that is a sample proportion. A sample proportion. Now, what's a proportion?
It's the ratio between the sample and the population.
Ish. So you're close. It is a ratio. It's the ratio of a certain quality out of the total number in the sample. So let's say I wanted to say, like, what is the proportion of people that have blonde hair in here? I would put the number of people that have blonde hair over the total number of people in here, or however many I sample, okay? And that would be my proportion of blonde hair in this room, okay?
So wait, that's L plus ratio, right?
Mm-hmm. Yeah, there you go. This notation is going to be new to you. It is p hat. P hat. Do you guys remember back in chapter 3? It's been a minute. Y hat. Do you guys remember Y hat? What is Y hat?
Estimated Y.
That's the estimated Y, right? So if we have a sample proportion of P hat, what do you think it's going to estimate? A population proportion of P. Very good. Very good. So P hat estimates a population proportion
Remember when I just randomly guessed that it was hat? Yeah,
of
that was-
P. I do. So here's the good news, you guys. These never cross. X bar. Its only job, whenever we use it in this way, is to estimate mu. S sub x is always trying to estimate sigma, and P hat is always trying to estimate P. So here's the kind of question you might get. What statistic do we use to estimate mean? Notice I never said the word sample, but what did I say?
Estimate.
I said statistic. And anytime I'm talking about a statistic, that has to come from a sample. Here's the good news. Statistic and sample both start with an S. Parameter and population both start with a P. Okay? So, what statistic do you use to estimate mean? X bar. What statistic do you use to estimate standard deviation?
S of X.
S sub x. What statistic do you use to estimate a proportion? P hat. What parameter do you use to estimate mean? Mu. What parameter do you use to estimate standard deviation? And what parameter do you use to estimate a proportion? So notice I never said the word sample or population. Sorry, I never said sample or population. So just knowing that parameters talk about the population and statistics talk about the samples, that's how you know which one you're dealing with, okay? So y'all are going to start seeing a little bit different words. It's just different words. It's like saying a boy and a man, right? They're pretty similar, right? All right? But, you know, just slightly different words, okay? All right, cool. Next, let's do some examples. Identify the population, the parameter, the sample, and the statistic in each of these settings, okay? Now, the population and the sample, it's the who or what. Who or what is the population? Who or what is in the sample, okay? The parameter and the statistic is the actual, like, notation that you're using.
I have a question.
Yes.
Right here it says sample statistics. Isn't that the same thing?
So,
It's like,
so the sample is who or what are you talking about? The statistic is what actual value are you going to get? Okay? Exactly. All right, so population, we need a parameter, we need a sample, and we need a statistic. Okay. All right, and so here's our first example. The Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. The first thing you need to ask yourself is, does this look like a problem that has to do with means, proportions, or standard deviations?
Proportions.
Proportions, why?
because it's a part of.
A
Because
part of
160
a whole. Very good. So this whole problem is going to be about proportions, okay? Perfect. Now, who or what is the population that we're talking about here? The population is the U.S. adults. So then what's the 515?
Sample.
That's the sample we took. So 515 selected adults, that's the sample. Okay? All right, now we already talked about that this problem seems to be wanting to do something with proportions, a part out of a whole. Okay? So what parameter would I be using?
That the adults cannot be ghosts themselves.
So remember, I'm asking you about what notation am I using for a population proportion. That's P.
What? I'm sorry, what?
The parameter that I'm using to estimate the proportion is P.
Okay.
Just like I asked you a minute ago. What parameter am I using to estimate a proportion? P.
So are these two literally just a sign and that's it?
Yes. Well, sort of.
Well,
Because now P we don't know for sure yet, because we don't know if we got a really good sample or not, but for now it's P. All right, what is the statistic that we actually did get told to us in the problem? Now, what statistic estimates P? What statistic estimates P? P hat. But we were actually told the numbers. So we can say what P hat was. It was 160 over 515. Do I know the actual population proportion? Not really. I probably, if this is a good, simple, random sample of U.S. adults, then I'm going to let this estimate that maybe later, once I know for sure I did a good sample. But for now, I do know that this is my sample value, and I'm trying to estimate a population value. Let's try it again. We got 2 more of these to try. All right, so again, we want to know the population, the parameter, who's the sample, and what's the statistic. These are the 3 things we need to identify out of this problem. Okay? So, here's the problem. From a large group of people who signed a card saying they intended to quit smoking, 1,000 people were selected at random. It turned out that 210, or 21%, of these individuals had not smoked over the past 6 months. What kind of problem does this sound like? Mean, standard deviation, or proportion?
Proportion.
Sounds again like we're looking at a proportion out of a total that has this quality. Okay, so again, we're going to be looking at P's and P hats. So actually, you guys already know the parameter and the statistic because you just identified that this is a proportion problem. You automatically know that this is P and P hat. Done, right? Okay, what is the population here? The large group of people who signed this card. It's literally just the large group of people who signed this card. Okay. And who's the sample?
1,000.
That's the 1,000 people selected. Good. And the only thing that we know additionally is we actually do know the p-hat value. What is the p-hat value? 210 over 1,000. You could also say that it's 21%. You could also say it's 0.21. All of those are equivalent.
Can you add 210 over 1,000 to the normal P2 by parameters?
Not until I know for sure that this was a good representative, simple random sample of the population, and I feel confident enough that it is a good estimate of the truth. Which, again, that's kind of where we're heading, but for now we don't know that for sure.
Okay.
Okay. All right, one more. Y'all seem to be getting this pretty well. Again, population, parameter, sample, and statistic. Population, parameter, sample, and statistic. Here we go. On Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from that day's production. The bottles contained an average of 19.6 ounces of iced tea. What kind of problem is this? Means problem. Perfect. This is a problem about means. So, what is the parameter for means? Mu. And what is the statistic for means? X bar. Perfect. Look at y'all. What's the population for this problem? That day's production of bottles. Very good. So it's basically all the bottles that day. Okay, so that day's bottle production. Good, very good. And what's the sample? The 50 selected bottles. Perfect. Now there's one more thing we do know. We know the X bar. We know the mean of the sample. What is the mean of the sample? Now, there's a problem. Well, there's not a problem, but what's that 20 about? That's what it's supposed to be. But when we took our sample, we only got 19.6 on average. Does that mean their machine is broken?
No, that means we got an interesting sample.
We got an interesting sample. And what is that called when our sample's just a little bit off of what it's supposed to be?
Standard deviation.
What'd you say? Did you say standard deviation? Ish. Look at the next question.
Sampling.
It's called sampling variability.
Sampling variability?
Yes! Did you know that if I took another 50 bottles and averaged them, I would probably not get 19.6?
You would probably
And I
get
would probably not
20.4.
get 20? I would get something maybe slightly different, maybe 19.8, or maybe I would get 20.05 or whatever. I should be around 20. What happens if I take a sample of 50 and I get an average of only 10 ounces?
Then your machine was probably broken.
Now I think the machine is broken, or somebody did a little something before they tested the bottles. Maybe they drank some of the tea. They were super thirsty. Bottle testing is hard, I guess. But again, that's how I know if I'm off, is if I have a big difference from what is expected and what I actually get. That is sampling variability in action, you guys. Oh my gosh, isn't that cool? Yeah. Sampling variability. Repeated samples will vary some from each other. and from what is expected. That doesn't mean it's wrong. Correct. That doesn't mean it's wrong. It just means that there's some variability. But, like you guys just said, if I get something that's really different, then I get suspicious, okay? So, a small difference is sampling variability. Small difference is just sampling variability. We have no issue there. That's just going to happen anytime you're taking samples over and over and over again. But if you get a big difference between what is actually true or what is claimed and other samples you've taken, that should be a red flag. Maybe a machine is broken. Maybe there's bias. Maybe our sample was just really, really bad, okay? And we'll talk about how to tell that later. That's like the next unit, okay? But that's where all of this is going. We're going in the same direction this whole semester, so it's really nice. Okay, cool? Cool. So far, this is easy, right? Heck freaking yeah. All right, let's define a sampling distribution, and then I'm going to show you a visual. All right, sampling distributions. A sampling distribution is the distribution of all possible combinations of the same size.
Do you have this memorized?
Uh-huh.
Like how?
From the same population. And this is my 9th year to do it.
That makes it 45 classes.
45 times.
Do you teach regular stuff?
I do. I have one class.
Like, would I be able to get regular stuff next year?
You're not supposed to, but you can.
Why would you
If you pass it on.
All right.
What if I
Sampling distribution is the distribution of all possible combinations of the same size from the same population. So wait. The Arizona Iced Tea Company, you guys. How many bottles of tea do you think that they produce in a day? Quite a few. So we take a sample of 50 and we get an average of 19.6 ounces in those 50, right? Okay. Then we have to go do it again and get another average. And then we have to do it again until we have gotten all possible combinations of size 50 from that entire day's production. How long is that going to take? Forever. Okay? So here's the good news about sampling distributions. They are simulated using computers. Because you don't have time to do that. Okay? They are simulated. They are simulated with statistical software. Okay. Why is there an entire chapter about them? What are they doing for us?
Making learners of the English language confused?
Yes, that is true. They are going to help estimate population values. And they're going to test claimed values. So the Arizona Iced Tea claims that they're putting 20 ounces in your bottles, but are they really? We can test it using a sampling distribution. So let me show you guys how the simulation works by using a little example here. And then we will probably be done at that point. We'll see. We'll see where we are. Okay.
Is my IST plotting against me?
Is what?
My IST plotting against me?
No, never. Okay, you guys, so I found this bag, okay? And in this bag, there's a whole bunch of marbles, okay? There's a whole bunch of marbles in this bag.
Is the bag replaceable?
Some of them are red and some of them are blue, okay? Now, here's the deal. Here's the issue. That is the population, right? This is a population of marbles, and half of them are red and half of them are blue. Are you with me? Now look, this is cheating because this graph tells you how many blues there are and how many reds there are, doesn't it? There's 100 of each. And so what proportion of them are red? 50%, right? Now, if I found this bag earlier today, did I know that there were 200 marbles if I just happened upon this bag? No. So usually in the population, I don't know this information. I don't know how many there are, and I don't know what the population value is usually, okay? So I don't know this information. So what do I need to do in order to figure out this information?
Thoroughly gerrymander the population.
I could absolutely do that, or I could dump out this entire bag of marbles and count all of them and figure it out, right? But I don't have time for that crap. So here's what we do. We take a simple random sample of 20 marbles, okay? So I'm going to let my friend over here, Serene, please take a simple random sample of 20 marbles from this bag.
They're totally marbles.
Yeah, I know. Go ahead and take one out.
Okay.
Okay. All right. So she has a simple random sample of 20 marbles. And Serena, can you count how many red marbles you just got?
Like 8 apparently.
Okay. So she just took a sample of 20 marbles out of this bag, and she counted how many of them were red, and she got 8 of those 20 were red. That means that Serena got 40% or a p-hat of 0.4. So I would go over to this blank dot plot. You guys don't see anything here, right? There's nothing there. And I would put a p-hat for Serena's sample proportion. Are y'all with me? Do you think that 40% is exactly the proportion of red that's in that bag? Why not? Why don't you think it's exactly the same? Because what could have happened when she took her sample? There's some sampling variability.
Yeah, like she got a Kit Kat, not 20 marbles.
What? Okay, now my friend Ebby is going to take a simple random sample of 20.
You're really demonstrating variability by having them take Skittles out of the bag full.
Now, please take a simple random sample of 20 marbles, Ebby. Now, Ebby,
It can also be cheese crackers.
your simple random sample of 20 marbles, how many of them were red? 11 of them were red. So you guys, look, this is so cool.
Republican-controlled Congress?
She got a p-hat of 0.55. Why is Ebby's p-hat different from Serena's p-hat?
Because a certain party wants to hold on to power.
Sampling variability. Hey, you guys, I'm going to put Ebby's p-hat on the blank dot plot. And guess what? We're going to do this again.
Choose me. You've been paying attention so long.
Now, we need another SRS. Jordan. Jordan, please don't mess this up. Jordan, please pick 20 marbles out of the bag. Now, Jordan, how many of your 20 marbles are red?
12 because you got a Kit Kat.
13. Wow, you guys, look. Jordan got a pea hat of 65. Why is Jordan's different than Ebby's and different than Serena's?
Because they got crackers while those two got Kit Kats.
Sampling variability. So, Jordan has one here at 0.65. Now, you guys, we have to do this every possible sample of size 20. Do you guys know that that's what these little dots right here mean? It does not mean someone's trying to text you back, okay? Those little dots right there. That means do that forever and ever and ever until you have all the pea hats of all possible sizes of size 20. So, pea hat, pea hat, pea hat, pea hat. Now, some people get the same pea hat as other people. Some people get a very different pea hat, okay? Are any of the pea hats a little bit different from everyone else's? Like a little farther away than everyone else's?
Likely.
Wow. So look at that. What is this? So look at that right there. 0.15. Why is that so far down from what everybody else was getting?
Because it's so different.
Possibly some really crazy sampling variability. Or what if that was Luke? And when he went to take his sample, he peeked in the bag and stayed away from the red marbles. What if he had some bias there? Well, we could use this to see what's the probability of getting this low of a result. It would be very small, okay? All right, that is the intro to sampling distributions.